The first experiment we're going to do is to determine the specific heat of a metal. And specific heat is just the relationship between the amount of heat gained or lost and temperature change per gram of the substance. Anyway, we need to pay attention because in this experiment there are two places that you have water and you can't get those confused. The first is the boiling water. We have a test tube down in the boiling water, and inside the test tube we have some pellets of a metal. And the whole reason for the boiling water is to heat up the metal. So what you will assume is that the temperature of the boiling water is equal to the temperature of the metal, and I'm going to put a 1 for initial, the initial temperature for the metal. Okay, so we have it down in there to get it hot. Water in our calorimeter, and we will need to know the mass of this water because this is the water that is going to warm up, and we're going to use our equations on this water. Okay, also on this we have our initial temperature of this water. So this is the T1 of the water. We'll take that. Okay, and so at this point we have some water in a calorimeter cup, which is basically a styrofoam cup. We know its mass and we know its temperature, and we've heated up our metal. We know its temperature, and then basically you dump this metal into this water. So when you dump the metal in, immediately heat is transferred because the metal is hot. And heat is always transferred from hot to cold. And that transfer will occur until the temperature of the water and the metal are the same. We call that thermal equilibrium. So that's important because that means that T2, or the final temperature of the water, is equal to T2 for the metal. So this top equation is the main one that we're going to use to relate heat, change in temperature, mass, and specific heat. Let's label these. So heat is the movement of thermal energy. Specific heat is the amount of heat required to warm or cool a substance by 1 degree Celsius. You will need the specific heat of water. I'll give it to you in a second. And you're going to determine the specific heat of the metal. So this M is for mass. And this T is the change in temperature. And sometimes we'll say delta T is final minus initial, which is fine, but I tend to say T2 minus T1. Now, one thing in this lab report, they don't want you to enter negative signs on wet lab flow. So that kind of bothers me because the negative sign has meaning. But so just something to keep in mind, that you're not going to enter negative signs for delta T's or Q's. So let's look at the equation for water because you'll do it first. You have all the information for water. Okay, we're going to look for the Q for water. The specific heat for water, it's given on the table 1. And it's given in calories per gram degree C. So we're using calories in this experiment. The mass here is the mass of the water in the calorimeter cup. It's not the boiling water, it's the mass in the calorimeter cup. The T2, remember that this T2 is for after the metal has been in the cup for a while. So just kind of note it's the same for both. T1 for the water, it gives you as the initial temperature before you added the hot metal. And this again is the calorimeter metal, or calorimeter water. Before we show the calculation for the metal, I want to remind you that if the metal is hot and it's giving heat to the water, whatever amount of heat that the metal is losing, the water is gaining. So that Q, the number, whatever number that is the same for both. Now, like I said, we know that really that would be a negative number for the metal because it's losing it, and a positive number for the water because it's gaining it. But like I said, they don't want you to put the negatives on there. So it's the same amount of energy that the metal is losing as how much the water is gaining. So now we can look at the calculation for the metal because we're trying to get to this. This is our goal, our specific heat of our metal. So the thing is that I was just showing you is that whatever number we get here, we're going to use here because the same amount of energy is transferred either way. Again, we're ignoring the negative sign, so don't worry about the negative versus positive for this. Okay, this is, of course, the mass of the metal. And then remember that our T2 is the same for both metal and water. And then this T1, this is a tricky part. Remember, this is the temperature of the boiling water. And it's not exactly 100 degrees C. You have to see what your given is. But remember, this is the metal's temperature, but the metal was dunked down into that boiling water, and so that's why we use the temperature of the boiling water there. So if we plug in everything I've showed you in orange, then basically you can solve for your specific heat of your metal, and it will come out in calories per gram degree C. And I didn't mention that here, but because we're using calories for in our specific heat, this will be in calories. Our Q's will be in calories. Okay, and that's how the units work. Okay, so that's how that one works. Now we're going to determine the calories that are in some food. And what's interesting is that if you burn food by lighting it on fire, the same amount of heat is given off by that, theoretically, as if you eat it and you digest it, because your body is doing the same reaction. It just does it in a lot of different steps and doesn't use a flame. But anyway, so the setup on this one, we have a can with water in it. And like before, you will need the mass of the water. Because once again, we're going to keep track of how much the water heats up and figure out a Q from that. So we have a can with water, and then underneath it, we have on a little wire a piece of food. And you'll know the initial mass of this food. And then you literally light the food on fire. I haven't done this experiment this way. You would light it off to the side and put it under really quickly. And the heat, of course, from the food burning is going to go up into the water. After the food stops burning, there may be a little food left or maybe some ash. And so you'll need to know what this final mass is, because you're going to figure out how much energy it gave off per gram of food. And of course, afterward, your water is going to be warmer. And so you'll need to have that temperature. So you'll start with the water again. The specific heat of water is that 1.00 calories per gram degree C. The mass of the water, that's the water in the can. And you got that at the beginning by subtracting off the can from the two of them together. And the change in temperature for the water, of course, that is just a final minus an initial. And you don't have other temperatures this time, so that's pretty straightforward. Okay, so once you get the Q for the water, remember, just like before, this energy came from somewhere. This came from, it's the energy from burning the food. And it will come out in calories, and they have you convert it to kilocalories. Of course, 1,000 calories in a kilocalorie. And the reason that you do that is because food calories, like if you look on a package, those calories are in kilocalories. To a dietitian, a kilocalorie is a calorie. It's kind of confusing. Okay, and the other thing they do is they want you to put it in kilocalories per gram of food burned. And so what you're going to do is the mass of food burned. You're going to take that final mass of food that you had minus what you started with. And this could have ashes in it or whatever. And once you get the mass that was burned, you can take however many kilocalories you had and divide it by the mass burned. And that will give you some number of kilocalories per gram for the food. And last, just some constants that you use along the way and a conversion that is a little bit tricky from what they give you. Anyway, the specific heat of water, 1 calorie per gram degree C. Of course, you can change that to kilocalories. This second one is really the one that I really wanted to show you because of the way they gave it to you. If you have this is like a specific heat in calories per gram degree C, to get it to joules per gram degree C, basically you're multiplying by this 4.18. And that's all you need.